Hi there, this is MG5004 and DE5418, Topic 6. This is the second class for Topic 6 on complex numbers, and this is where we look at Moivre's theorem. We already know how to multiply in polar notation and, well, any of the forms that we've got. So if we've got z equals r e to the j theta, and we know that z is equal to cos, that's a theta, plus j sine theta, and that z equals r angle theta, then if we think about it, say z1 times z1, which is the same as z1 squared, is going to be r1 times r1 angle theta 1 plus theta 1. So that was r1 squared angle 2 theta 1. And you could see that we could just go on forever. So what we've got here is that z to the power of n equals r to the power of n angle n times theta. Now, this allows us to do some quite interesting things. For example, we can now evaluate -7 plus j to j5, which is a complex number, to the power of 4. Let's work out the inner bit first. -7 plus j5 is equal to, do the calculation, it's the square root of 7 squared plus 5 squared, the square root thereof, that's 74. Angle, and we can work out the angle, the argument, and that's in quadrant 2, like that. So, oops, not big enough, that would be -7, and that would be 5. What we're going to do now is take it to the power of 4, so now we've got, what are we doing? We've got root 74 angle 144.6 to the power of 4. So Moivre's theorem tells us that the complex number to the power of 4 is the modulus to the power of 4 angle 4 times the argument. Let's work that out. Root 74 to the power of 4 would be the same as 74 squared. And 4 times 146 would be 500 and something, 577.84. Now, if we were considering that theta was between 0 and 360 degrees, then we'd have to rewrite that slightly so that it was 5476 angle. Okay, so we take off 360, 577 minus 360 would give us 217.84. And then what we could do is we could rewrite that as, what am I doing, as 5476 times cos, I don't need a bracket there, times cos of 217.84 plus j times 5476 sine of 217.84, and working that out, or we could have just gone directly from polar form to rectangular form using our calculators. It's actually more normal to look not for powers but for roots. So we can either use form 1 or the exponential form as written as 2. It makes no difference, they are the same things. And there should be a sign in there, there should be an angle sign in there, like that. Let's look at finding the cube root of the given complex number. So what we're looking for is z to the power of a third. What we've got is that z is equal to 8 angle 120 degrees. Now, we could think that theta was just one revolution plus 120 degrees, and the vector that we've got there would still be in the same place if we went 2 revolutions plus 120, or 3 revolutions and 120. So 2 revolutions plus 120 would be 480, 3 revolutions plus 120 would be 840, and 4 revolutions plus 120 would be 1200, and so on. So we could write that z was equal to 8 angle 120, or z equals 8 angle, what do we say, 1 revolution plus 120, so that would be 480, or z equals 2 revolutions plus 120, or 4 revolutions plus 120, and so on. Okay, let's have a look at that. Let's take now, using the rule, let's take the cubed root. So it's going to be the cube root of 8 angle 120 over 3, or 8 to the power of a third angle 480 over 3, or 8 to the third angle 840 over 3, or 8 to the third angle 1200 over 3. So I get, no, cube root of 8 is 2 angle 40, or 2 angle 160, or 2 angle 288, or 2 angle 400, etc, etc, etc. But if we're looking at 2 angle 400, that's 360 plus 40, so we're back to the beginning again. That's the same as the first, so we don't need to include that one. So if we're going to draw that, that would be 2 and 40 degrees. The next cube root would be 160 degrees, and that's the length of 2. And the third root would be, so that's 280 degrees and a length of 2. And the fourth one is back to being the same as the first one. Now what we've got is that we've got 3 cube roots equally spread around the circle, or around the quadrant. And we talk about the principal root, the principal cube root in this case, as being the one that is closest to the x-axis. In this case, it would be the first one would be the principal cube root, because that's the closest to the x-axis. I will do some problems, some more of these on the board. Just remind me. So what we should be able to see from this is, let's look at the one we've just done, the cube root. Then a complex number has 3 cube roots, all separated by 360 over 3, which is 120. If there's 4 roots, it would be 360 over 90, so they'd be separated by 90 degrees. The fifth roots would be separated by 5, etc., and 2 square roots would be separated by 180, etc. Let's have a look at finding a slightly more complicated root. Here we've got that z is equal to -1/2 plus j to the power of 1/2. We could look that up and you could use your calculator, but it's going to be, we'd find pole of -1/2 and 1/2, and we'd find that z was equal to, the angle would be 135 and 2 to the -1/2. Or if we were doing it in pi's, oops, that's a 2, not a z. Okay, now we've got cube roots, so they're going to be equally spaced. And they'd be equally spaced by 120 or 2 pi by 3. So z is equal to, z1, say this is the first root, would be equal to 2 to the power of -1/2 to the power of 2/3, angle 3/4 pi, let's do it in pi's, times -2/3. That's the first root. Then the second root would be 2 to -1/2 to the 2/3, -2/3, because the length is always going to be the same, angle 3/4 pi times -2/3, but this time it's going to be another 120 degrees on, or another 2 pi by 3 further round, because the roots are equally spaced. And the third root will be the same length, and this time it'll be yet another 120 degrees, or 2 pi by 3 round, which would be 4 pi by 3 added on. So if we look at each of those in turn, then the first one will be 2 to the power of 1/3 angle -pi by 2. And if we were to rewrite that, we would write it as 2 to the 3rd cos, depending on how you wanted your answer. And the second one would be 2 to the power of 1/3 angle 1/6 pi, which we could rewrite as cos of 1/6 pi. And the third root would be 2 to the 3rd angle 5/6 pi, which we could rewrite as 2 to the 3rd cos 6 5/6 pi plus j sine pi by 6. And this is pictured on the next slide. The principal root is the root that's closest to the x-axis, and in this case it's the one that I called Z1 on the previous slide. We've looked at all of these. Remember, this is Z to the negative 1 is 1 over Z, which is 1 over cos theta plus j sine theta. And remember, we multiplied that out so that we got the result here, cos theta minus j sine theta. Now, the whole of this thing does allow us to expand sine to the power of 4 theta, and it allows us to find things like cos 3 theta and sine 3 theta and so on. And if you also recall back to the binomial series expansions, the one that allows us to work out quickly brackets like that, then you'll see exactly where we're going. Look at it on a new slide. I'll do the first one here, but I'll do the second one in class. To find cos theta and sine theta, what we need to start with is that cos of 3 theta plus j sine 3 theta is equal to cos theta plus j sine theta cubed. Now, we can expand that using the binomial theorem, binomial series expansion, so that what we've got is, now I have to write pretty small. In fact, maybe I will just use C's and S's for sine. So, all right, cos 3 theta, cos of theta, I'm just going to write as C, and sine of theta, I'm going to write as S, just because I've not got enough room. So C cubed plus J 3C squared S minus 3CS squared minus JS cubed, because J squared equals negative 1 and J cubed equals, it's a negative J. Now if we equate the real parts, so the real part would be cos theta, so the left hand side gives us cos 3 theta, and that's got to match up with the non-j bits, if you like, from the right hand side. So cos 3 theta is going to equal, I'll write it out in full this time, cos cubed theta minus 3 cos theta sine squared theta. And doing similarly with the imaginary part, then sine 3 theta. So I need to find the imaginary parts on the right hand side, so it would be that bit and that bit. So sine 3 theta equals 3 cos squared theta sine theta minus sine cubed theta. Now we know that sine squared theta is 1 minus cos squared theta, so sine squared theta equals 1 minus cos squared theta, and we know also that cos squared theta equals 1 minus sine squared theta. So we could actually collect all of that up and write that cos 3 theta is equal to 4 cos cubed theta minus 3 cos theta, and that sine 3 theta equals 3 sine theta minus 4 sine cubed theta. Now, these are useful results in themselves, but the method is more important. Sometimes it's quite useful to be a little bit devious, a little bit smart. We know that Z equals cos theta plus j sine theta, if we call that equation 1, and we know that 1 over Z is equal to, well, it's equal to Z to the negative 1, is cos theta minus j sine theta. So we know that. If we add them together, then we get z plus 1 over z is equal to 2 cos theta, just by adding 1 and 2. And if we were to subtract 2 from 1, then we would get z minus 1 over z is equal to 2j sine theta. Also, while we're here, we may as well look at what z to the power of n is. It's cos n theta plus j sine n theta, and 1 over z to the n must be z to the negative n, which must be cos n theta minus j sine n theta. So what we need here is these two results here, and we will use them to expand cos cubed theta. For example, let's have a look at the first one, cos cubed theta. Now again, we start in an odd place, and once you've seen it done once, then you know where to start. We know that z, let's change my color, z plus 1 over z is equal to 2 cos theta from the previous slide. So that means that 2 cos theta cubed is the same as z plus 1 over z cubed. Now again, using the binomial expansion, we get that this is equal to z cubed plus 3z squared times 1 over z plus 3z times 1 over z squared plus 1 over z squared. And if we tidy that up, we get z cubed plus 3z plus 3 times 1 over z plus 1 over z cubed. And if we were to collect all those up, what we've got now is that 2 cos theta is equal to z cubed plus 1 over z cubed. Do you see where we're going? Plus 3 times z plus 1 over z. Now, we know that z plus 1 over z is 2 cos theta. So z plus 1 over z equals 2 cos theta. And we also know that z cubed plus 1 over z cubed must be equal to 2 cos 3 theta, just by substitution. So now, this is what we've got. We've now got, whoops, I've lost a cubed. So now we've got that 2 cos theta cubed equals 2 cos 3 theta plus 3 times 2 cos theta. Okay, remember what we're looking for. We are looking for cos cubed theta. If we expand the left-hand side, now we've got 8 cos cubed theta equals 2 cos 3 theta plus 6 cos theta. We didn't want to find 8 cos cubed. We wanted to find cos cubed. Now I'm just going to do it in 2 steps. Just humour me on this one. Let's just divide it by 2. So we've got 4 cos cubed theta equals cos 3 theta plus 3 cos theta. Now I'm going to divide it by 4. Just easier to see with the fractions that now cos cubed theta equals 1/4 cos 3 theta plus 3 cos theta. And we're done. Now, I won't do the next one because the next one's an assignment question, but if you follow the same method, you won't have any difficulty. I will do the first one here, and we can do the second one in class. First up, let's take a common factor of x out of the first one. So now what we've got to do is factorize the inner bit. Now it's a quadratic, but I don't think we can factorize that. I can't think of any numbers that will multiply together to give us 169 and add to give us 10. So what we can do, and this is not to be recommended, but we can do it if we're careful. We can cheat a little bit. We can find the roots, and then because you know how these things work, you can then create the factors. You know, this is what we're trying to do, that if you've got the roots are x equals negative a and x equals negative b, then the brackets must have been x plus a times x plus b. So that's what we're going to do here. We're going to find the roots and then create the brackets. So using the quadratic formula, x is going to be equal to negative 10 plus or minus the square root of 10 squared minus, oops, that's squared, times 1 times 169 all over 2. And if we push that through the calculator, it's negative 10 plus or minus 24j over 2, and that's equal to negative 5 plus or minus 12j. So then x equals negative 5 plus 12j, or x equals negative 5 minus 12j. So now we need to create the brackets. So the brackets must have been x minus the first root and x minus the second root so the polynomial must have been x times, I'm just going to put a square bracket in there because we've got a lot of brackets, x minus negative 5 plus 12j times x minus 5 minus 12j. And you could tidy that up a little bit if you wanted to, but it's fine like it is. So I'll do the next one in class. I will do the second one, and I'll do the first and the third one in class. So let's have a look at the second one. I'll take a bit of space up here. We can say that z to the 4 equals negative 4. And if we put that on a set of axes, then we could write it that z was a length of negative 4. So that's z there. So that means we could write z as r angle theta. So we could write z to the power of 4 as r to the power of 4 angle 4 theta. As a complex number, we could rewrite negative 4. Negative 4 is equal to negative 4 plus 0j. And writing that must be 4 angle pi plus iterations thereafter. Now, this must be the same. So we've got that r for angle 4 theta must be equal to 4 angle pi plus 2k pi. And that 4 theta must be equal to the bit in the brackets, so 4 theta must be equal to pi plus 2k pi. Oops, 2k pi. So theta must be equal to pi over 4 plus 2k pi over 4, or theta equals pi by 4 plus, do the numbers, k pi over 2, where k equals 0, etc. Now, also equating that, r to the power of 4 must equal 4, because this bit must be equal to this bit. We've already said that this bit must be equal to this bit, so we did that down there. Now we're going to do this over here. So r must equal 4 to the quarter, which is equal to 2 to the power of a half. So z is going to equal 2 to the half angle when k is 1, sorry, when k is 0, and 2 to the power of a half when k is 1, and 2 to the power of a half angle pi by 4 plus pi, and 2 to the half angle pi by 4 plus 3 pi by 2, and anything after that we're starting again, and it also corresponds with the fact that we've got 4 roots as well. So if we put that on a diagram, the 4 roots would be 1, 2, 3 and 4, and the principal one would have been 2 to the half angle 45. Now this next bit is for the electrical students, and you know far more than me about currents and stuff, and voltage and current flowing through and the corresponding voltage, etc, etc, etc. So I will just look at some of the maths involved. What we've got in this situation is that V is equal to I over omega C sine omega t minus pi by 2, where the voltage is lagging the current by pi by 2, out of phase by pi by 2. I'm sure you electricals know that XL will be equal to 2 pi FL, and XC will equal 1 over 2 pi FC. And that tells us that V is equal to IR plus J omega Li minus Ji over omega C, and that's equal to IZ, Z, and Z is equal to R plus J omega L minus J over omega C, because 1 over J equals negative J. And we could go on further, and again I'm sure you know that V equals I modulus of Z sine omega t plus alpha. where omega z, sorry, where modulus of z is so that's the impedance of the circuit. The phase of the circuit would be now, I'm not teaching you any of that. You non-electricals don't need to worry about it. The electricals, you will have been taught this in something else. All of this is just facts. The resistor, the impedance of a resistor, the impedance of an inductor, and the impedance of a capacitor. Okay, let's get down to business here. Let's look at an example. The circuit shown on the previous slide. Again, this is not for anybody but the electricals. So we can work out that Z is equal to R, which if we convert to a complex number, and we can write it in polar form, and Z subscript L and put that in polar form, and ZC and that's 0 minus J10, which is 10 angle negative 90. So we know that Z total impedance so we've got 0 minus J10 plus 10 angle 0 times 10 angle 90 over 10 plus J0 over plus 0 plus J10, and if we do all that we end up with 0 minus J10 plus 100 angle 90 over 10 plus J10, and we can change the bottom line as well, so that's 0 minus J10 plus 100 angle 90 over, use our calculators, and we get 10 root 2 angle 45, which equals 5 root 2 angle negative 45. A little bit of number crunching in there, but not too much. Should be able to handle it. The last part, you're asked for the current. You know that I is equal to V over Z. So that's 50 root 2 is given, angle 45. Now divided by what we had, 5 root 2 angle negative 45, and we end up with 10 angle 90, which we could write as 0 plus J10. Again, this is only for the electricals. We need to find the angular velocity omega. Omega is equal to 2 pi f, 2 times pi times the frequency, which is 2 times pi times 10 to the 6. And we're asked to find the supply velocity. That would be 8 times 10 to the negative 3 angle 0, and we'd be looking at millivolts. And then the impedance would be R minus 1 over omega C, and we're given C is equal to, 100 picofarads, which is 100 times 10 to the negative 12, which is 10 to the negative 10. Just do that simplification first. So Z is equal to 12 minus 1 over 6.283 times 10 to the 6 times 10 to the negative 10, which equals 12 minus 1591.55. Let's make that a J, put my dot on my J. Then the current I is equal to V over Z, so that's equal to 8 times 10 to the negative 3 angle 0 over this number that we just had. And when we do that, we have 5.0264, don't forget the powers of 10, angle 1.5632 by dividing 8 times 10 to the negative 3 by 1591.595. For those that need it, we will do the circuit here in class. This is just a slightly different way of looking at things. So we've got that the force A is 10 angle 45. It's a length of 10 at 45 degrees. Force B is equal to a length of 8 angle 120. And force C is equal to a length of 15 at 210 degrees. And the total force is going to be them all added up together. So it would be 1045 plus 8 angle 120 plus 15 angle 210. And we can either convert them to coses and sines, or we can convert them into polar notation, and we could convert it back again. Our final answer would be that, and that's in the second quadrant. The magnitude of that is going to be the square root of negative 9.919 squared plus 6.499 squared, squared on the outside, which is 11.86 newtons, and the resultant force, the direction of the resultant force, is inverse tan of 6499 divided by negative 9.919. So the direction is 146 degrees.